Okay, so this lesson we are going to be going over Module 12. First we'll do the review questions, and then we'll break and we'll do the practice problems for this module. And then I'll have a few extra questions for you. All right, so let's start with the review questions. So number 1 says, define pressure and name 3 units associated to measure it. So pressure, if we're defining it, pressure is simply just the force per area, okay? So we could write it like this. So depending on what your unit area is, your term for pressure is going to change, okay? And then they ask you to name 3 units to measure it, and I'm just going to go ahead and list all of them, okay? So pressure units. And we've dealt with several this module. The first one is going to be the Pascal or the kilopascal. Okay, they're really the same unit, one's just bigger. All right, so that's the first one. The next one is going to be millimeters mercury. So little m, Hg for mercury. The next one, which we use quite a bit, is torr. That's another pressure unit. And our last pressure unit is going to be atmospheres, and we abbreviate it ATM or ATMS, okay? Atmospheres. So those are your pressure units. You're going to need to know those for the test. I don't think they make you know all of them, but you're going to have to know several, okay? Next one, it says, write Boyle's law in your own words. All right, so you can see Boyle's law is right up here, and they want you to write it in your own words. So really, if you look at Boyle's law, we know that the pressure and the volume, when they're multiplied together, that has to stay constant. So really, in essence, they're inverses of each other. So and keep in mind the volume, the temperature must stay constant because we don't have T in here. So temperature stays constant because it's not part of our equation. So we could really just say, well, when the volume goes up, the pressure goes down, right? Or if the volume goes down, the pressure must increase. Okay, they're inverses. So let's look at number 3. So that's Boyle's law. Let's look at number 3, Charles' law. It says, which one of the laws have you studied in this module that leads to the Kelvin temperature scale? So remember, Charles' law here, it's talking about volume and temperature. Remember when we were talking about Charles' law, how whenever the volume decreases, the temperature is also decreasing. And then we talked about how the temperature gets colder and colder and colder. It can only get so cold because it can't reach 0, because then there would be no volume left, so there wouldn't be anything there, okay? So in your brain, you're thinking, okay, that's Charles' law, and so if the temperature is increasing, volume increases. If the temperature is decreasing, the volume decreases. So that leads us to the Kelvin temperature scale, because the Kelvin temperature scale can't reach 0. It doesn't reach 0, okay? And it can't go less than 0. So that's the answer to that one. Number 4 says, what general rule must a careful scientist follow when extrapolating data? So we know when we extrapolate data, we take a bunch of data that we have, and we can basically make a prediction or a guess, an educated guess to what's going to continue to happen. But the general rule you must follow is you have to have a large amount of data and just a little bit of extrapolation. So you have to have a lot of that backing you up to be able to make a very small guess. Okay, otherwise it's poorly done. Number 5 says, what are the properties of an ideal gas? So, right here, let's move this guy over. Properties of an ideal gas. So we're talking about the 3 different things. What makes a gas ideal to work with, okay? So there's 3 different things. So the first one, let's say I have a volume here. The first one says molecules of a gas, or the atoms, they have to be very small compared to the total volume, okay? The second one says that those molecules or atoms have to be so far apart that there's no attraction or repulsion. So they're so far apart that they're not pulling on each other or repelling each other. There's no impact there, okay? And the third one, it says that they cannot, those molecules, they can't lose energy if they bounce into each other or off the walls, okay? So they're maintaining a constant amount of energy, so the pressure is not changing at all, okay? That's the whole idea. So those three things, if a gas meets those three criteria, then it would be considered an ideal gas. All right, let's look at number 6. It says, under what conditions do gases behave ideally? So these are what make a gas an ideal gas. And now they want to know under what conditions do they behave ideally? Well, let's do pressure and temperature. We know that a gas behaves really well when the pressure is 1.00 atmospheres or lower. We want that pressure to be low. And for the temp, we want it to be 273 Kelvin or higher. So really, we would say that we would want low pressure, high temperature, okay? And the next one's very similar to this. It says, what is standard temperature and pressure? Well, STP, standard temperature and pressure, is simply this, without this, okay? So it's ideal to have a low pressure and a high temperature, but STP is simply 1 atmosphere, 273 Kelvin. Okay, so you're going to need to know this because some of your problems are going to, instead of giving you your pressure and your temperature, they're going to say, and this gas was at STP. Well, you're going to need to know what that is, otherwise you won't be able to do the problem. All right, let's look at the next one. Number 8. Number 8 says 2 steel containers of equal volume contain 2 different gases at the same temperature. The first container holds 1.3 moles of N2 gas and the second contains 1.3 moles of SO3 gas. Compare the pressures of the 2 containers. So, real quick, let's put our so these have 1s, these have 2. We're just comparing the 2, okay? So they said they contain same temperature. So really, we don't need to worry about that, okay? So we're really just comparing the top 2. And they want to know the pressure, okay? So think about this. They have equal volume, and I've got 1.3 moles of each of these gases, okay? So if I know right away, if I have 1.3 moles of each, I have the same amount of each, okay? And we know from Dalton's law, over here, we know from Dalton's law that it tells us that it doesn't matter, when we're talking about pressure, it doesn't matter what the identity of the gas is. It doesn't matter if it's N2 or SO3. It doesn't matter what it is. It just matters how much you have of it, what quantity it is. So we have the same quantity, 1.3 moles. Therefore, the pressure is going to be equal between the 2. Okay? Let's look at 9. 9 says, a liquid's temperature is lowered from 50 degrees to 10 degrees Celsius. Then it says, did the liquid's vapor pressure increase, decrease, or stay the same during that time? Okay, so think about this. We're working with temperature and pressure. Okay, so I can go ahead and get rid of that. Okay, so we're just dealing with temperature and pressure. So think about it. Our temperature went from 50 to 10. So from here to here, it decreased, okay? And this tells us, using our equation here, that if this is going to decrease, this has to also decrease to be able to make sure that they stay equal, okay? So unlike our other law that we did, I think on like one of the first, I think it was the second one, number 2, it was an inverse. These are linearly proportional. So if one goes down, the other goes down. If one goes up, the other goes up. So this is going to be decrease. All right, last one, number 10. It says the mole fraction of nitrogen gas in compressed air is 0.78. If you have 1,000 molecules of compressed air, how many will be nitrogen molecules? So they said the mole fraction. So let's go ahead and just put that up here really quick. I know the mole fraction is just number of moles of the part over number of moles of the whole. Okay, so they gave us the mole fraction. They said it is 0.78. So I'm going to stick it in for this. Okay, and then they said you have 1,000 molecules of compressed air. I've got 1,000 down here. Well, I'm trying to find what the mole fraction is for that nitrogen. Okay, so really I'm just going to use algebra to figure this out. So now I've canceled over here. So if I can either type this into my calculator, or I can just go ahead and move my decimal point, which is what I'm going to do. Like that. I end up with 780 as X. And remember, X was the number of moles of that gas, which was N2. So that's going to be my answer, 780. All right, so let's stop there, and then we will start up with the practice problems.